Well, now that we've developed our transmission theory of the MOSFET, we can go back and easily update the virtual source model so that it accurately describes modern-day transistors. And that'll turn out to be very easy to do. Remember, we developed the virtual source model using a very traditional or diffusive model for the MOSFET. The linear region current involved a mobility, a traditional mobility due to scattering. The saturated current involved a high field saturation velocity due to the saturation of the velocity of highly energetic electrons under a high electric field. All right, this model is relevant for MOSFETs with very long channel lengths. Our level 1 virtual source model then smoothly connected the linear and saturation regimes. Well, we have a transmission model now that describes short channel devices all the way to the ballistic limit. All we need to do is to replace the scattering limited mobility by a quantity that we called the apparent mobility. It's not a fudge factor. It's not something that we just empirically adjust to fit data. It has a simple, clear physical interpretation. Our saturated current looks just like the traditional model, but the velocity has a different interpretation. The velocity is related to the transmission under saturated conditions and involves the unidirectional thermal velocity as well. So we can easily now take our virtual source model and make two changes. Where we had a saturation velocity, we replace it by this injection velocity. Where we had a scattering limited mobility, we replace it by the apparent mobility. We've introduced no additional parameters. There are still only 10 parameters in this model, so that makes it easy to use and to fit to measured IV characteristics. No more parameters. We've simply reinterpret two of the parameters that were already in this model. So what we're able to do now is to properly describe transport at the nanoscale. Let's take a very quick look at transport under low VDS and under high VDS conditions. Under low VDS conditions, we're describing transport through this apparent mobility. The apparent mobility is a combination of the scattering limited mobility and the ballistic mobility. Each of those is a well-developed, well-understood concept with clear physical significance. This combination of mobilities might remind some of you about something called Mathiassen's rule. In traditional semiconductor physics, when we have two different scattering mechanisms that are occurring at the same time, and we want the overall mobility due to those two scattering mechanisms, we combine the two mobilities by a prescription called Mathiassen's rule. That's exactly what we're doing here. We are combining the effects of traditional scattering, which are all inside mu sub n, with effects due to ballistic transport, which are described by the ballistic mobility, in an expression that looks exactly like Mathiassen's rule. Under saturated conditions, we bring in this injection velocity. And let's look a little more carefully at that. A key parameter is the transmission. And remember, the script L here is the length of the bottleneck region that the electrons have to get across in order to come out the drain and contribute to drain current. I'll also remind you that we have a simple expression for the diffusion current in terms of the unidirectional thermal velocity and the mean free path for scattering. Diffusion is random thermal motion. Well, we can use these expressions, and I encourage you to go through and show that we can write the injection velocity in this way. 1 over the injection velocity is 1 over the unidirectional injection velocity, the unidirectional thermal velocity of electrons, and 1 over d over L. D over L has the units of velocity. It's a diffusion velocity. Well, how do we make sense out of this result? Let's take a look at our band diagram under high VDS conditions. Remember, there's a bottleneck region that is a length script L long. That's the critical region that limits the current flow under high VDS conditions. Now, this looks something like the base of a bipolar transistor, for those of you who are familiar with bipolar transistors. It looks like the thin base of a bipolar transistor, and electrons have to diffuse across the base in order to contribute to the collector current. The drain looks a lot like the collector of a bipolar transistor, which collects the current, the electrons that diffuse across the base. And the source looks a lot like the emitter, which injects electrons into the base of a bipolar transistor. Here we have a source, and electrons are injected from the source over the barrier, into the top of the barrier in this bottleneck regime. So that bottleneck regime is really the very important region that limits the current, just like the base limits the current in most bipolar transistors. And the way we interpret our expression for the injection velocity is that it is the slower of the two velocities, of the ballistic velocity and of the diffusion velocity. If the rate limiting process, the limiting process is electrons diffusing across the thermal velocity, across the bottleneck regime, that diffusion velocity will be low, and that will determine the overall injection velocity. If that velocity is very high, unphysically high, because electrons can't diffuse faster than the thermal velocity, then it's the unidirectional thermal velocity that limits the injection velocity. In fact, this expression was developed by device physicists in the 1970s when they were describing electron transport in very thin base bipolar transistors. In the 1970s, device physicists were already considering ballistic transport in bipolar transistors, and we find something very similar is occurring in modern day MOSFETs now that their dimensions are comparable to a mean free path. So with that simple replacement of these two traditional parameters by two new parameters, our virtual source model accurately describes modern day MOSFETs. In the next lecture, we will apply the virtual source model to some measured data, and we will see how we can learn something about transport in these modern transistors through this analysis. That'll be the subject of the next lecture.